Hello everyone. In the last video, I said that I would upload the code for interrupt. So that's what I have done in this video. I have explained how I wrote the code, and also you can check my code in the GitHub link which I have given in the descriptions or comments. So yeah, enjoy. The way I wrote the code for interrupt was basically make some changes in the init function, or I can say I have had some code in the init function. Like previously, it was till the GPIO handling only. Now this is the else block which I have written, which basically handles the interrupt. So before that, I like to take you to the driver.h, where you can see there are different modes here, and each modes have been assigned a specific number. So as you can see, when the GPIO is acting as an input, it has given macro 0. If it is acting as an output with a speed of 10 megahertz, it has been given as 1, 2, 3, so on different. But as you see, if you go above 3, like the 4, 5, 6, you can see these three modes are only interrupt, right? Means I can say that if the mode given by the user is greater than 3, then short it will be for interrupt. And if the means if this number is less than 3, sorry, if it is less than 4, then short it is acting as a normal GPIO. So yeah, that's what I have done here. Basically wrote this big if block, uh, like these blocks where I check whether the mode is less than GPIO mode out speed 50, meaning that if it is less than equal to 3. If it is less than equal to 3, then I know that the GPIO means the pin is acting as a normal GPIO. But if it is more than 3, then definitely it is acting as a interrupt, right? So that's what I have done in this else block. Wrote the code for interrupt. So now, as you can see here, there are some bits I have defined: bit 0, bit 1, bit 2, bit 3. So you might ask, what are these bits? Like, why we have to define bits, and what is this modulus 4 into 4? So for that, I'll take you to the AFIO registers, which you can see in the reference manual. There is a section called as AFIO configuration register here. You can see like it is configuration register 1, then 2, then 3, and 4. So there are total 4 such registers, and as you can see, it consists only means first 3 pins, or I can say, sorry, not 3, 4, means 0 to 3. Then the next register contains 4 to 7 pins. Then the next contains 8 to 11, and the last contains 12 to 15. So all these 15 pins are being configured using these AFIO registers. So what happens is, this will help me enable the EXTI line. Suppose I want to enable the EXTI 1 line for port B, then I will write this 00001 in this port B. Suppose if I want to enable EXTI 3 line for my port C, so I will write 0010 on these bits. So you can see that I'm means focusing on 4 bits, right? I'm writing on these 4 bits, and also I'm making sure the track of pin number, like if the pin number is less than if the pin number is less than 4, then I'm configuring this. If the pin number is less than 8, then I'm configuring this. So that's what I have written here. If pin is less than 3, if it is less than 7, if it is less than 11. So that's means there are different registers I have been configuring. And for the bit part, like it uses some simple math. Like if I suppose want to configure pin 1, so what I'll do here is I will first make the modulus of means 1 modulus 4, which is 1, and then multiply it by 4, which means 4. So I know that I have to start from bit 4 and go till bit 7, means bit 1, bit 2, bit 3, which are basically just this 4, 5, 6, 7. So I'll know that I have to configure 4, 5, 6, 7, these 4 bits for configuring my pin 1. And yeah, that's what is done inside the if block. I have configured it. No, sorry. Firstly, I have cleared all those bits. Means before configuring for a specific port, I have clear. Like as you can see here, and equal to this not expression, means I have first cleared the whole register. If it is for pin less than equal to 3, I have cleared this AFIO register. If, else I have cleared this AFIO register, else this. Once it is cleared, then I am looking which type of triggering mode is there. Like we know that there are three types of triggering mode. First is rising triggered, then falling triggered, then there is a level triggered where we act on rising as well as falling. So that's what we have configured down below. But yeah, first before writing some values to it, I cleared them because we don't want to some floating values just to make our code safe. So yeah, this basically logic has been used to know which bit we are configuring and which bit we want to change. Suppose if it is a bit, suppose if I want to configure pin 8, right? So pin 8 will be in EXTI 3. So what I'll do is I'll do 8 modulus 4, which is 0, and 0 into 4 is 0. So I'll know that I have to configure bit 0, 1, 2, 3, like that. So it's basically a what you can say mathematical logic to know which bits we need to configure, and which register we are configuring, that is decided by this pin number. I hope you get it. Okay, so once we clear the AFIO registers, now we need to check which mode is the user talking about. If is it about rising trigger, or is it about some falling trigger, or is it about some level trigger where we observe both rising and falling. So yeah, that's what is done in this if block. Basically, first we'll check which port the user is talking about. Is the user talking about port A? If he is talking about port B, or if he is talking about port C. So depending upon different ports, we'll be configuring different registers. So that's why there are multiple if blocks as seen here. Like suppose if I want to configure the port A, so I'll write 0000 to all, means suppose if I want to configure this EXTI 10 port A, so I'll basically write 0000 on all these 4 bits. And suppose if I want to make interrupt for port C on this EXTR10 line, so I'll write 0010 on this bit. So that's what is done in the code. Like for GPIO, I don't need to write anything because I have already cleared it. And for again, I don't want to clear them again because it's waste of time, right? So when I don't need to clear it again because the port A requires only 000. But for other ports, I have to do it. Like suppose if it is for port B, so you can see for port B, I have to write 0001. So depending upon which pin the user is talking about. If the pin is less than equal to 3, then as I said, configuration register 1. If it is less than equal to 7, then configuration register 2. Or if it is less than 11, then 3 or 4, depending upon which pin he is talking about. So like for writing 0001, I'll just make the LSB as high. That's what is done here. Basically, I am configuring different registers, right? So that's why I have to use a if block. Else I could have just wrote in a one line. And these are two new lines you might see. There is something like EXTI IMR, EXTI RTSR. What is this? So for that you have to go to the interrupt section in the reference manual. Interrupt, and you can see here a interrupt mask register, which means that if I want to enable, if I want to use that GPIO pin as an interrupt, I need to make this mask register bit high so that the processor gets to understand whether I am using this pin as interrupt or not. So suppose if I am using pin 3 as my interrupt, so I need to make that bit 3 high. So depending upon the pin user has given, I'll make that bit high from the mask register. So yeah, you can say that if this bit is not high, then that pin won't act as a interrupt. Sorry, that pin won't act as an interrupt. To make that pin act as an interrupt, I need to make the mask register high. And since the interrupt is of type rising trigger, means whenever the button goes from low to high state, then the interrupt needs to be triggered. So there is a register called as rising trigger selection register. For means if I want to enable that GPIO pin interrupt as a rising trigger, I need to make that bit high. Suppose I want pin 6 GPIO as an interrupt. So first I will make the mask, means the mask register bit 6 high, and then if I want to use that interrupt as a rising trigger, so I'll make the bit 6 high. And suppose if I don't want to use it as a rising trigger, if I want to use it as a falling trigger, then I'll make the bit 6 of the falling trigger register high. So I hope you get the difference. So which register to make high or low. And yeah, same for GPIO-C, just the registers are different and some values are changed. Same for the falling trigger. Yeah. And my board means I'm using STM32 Blue Pill, right? So it only has two ports, means yeah, it has port C, but very less amount of pin. So I don't need to define for other GPIOs. Well, if you are using some other discovery board or more costlier board, then yeah, you need to define for others too. Same for rising falling trigger where I basically make the bits of rising register and falling register high so that I get interrupt on two states. So yeah, this is what is done inside the init. So basically, in short, if I have to summarize, we recognized first which type of mode the user want. Depending upon that, we first clear the AFIO registers, then configure those AFIO registers as per the port which the user needs, and then depending upon whether he wants a rising trigger or a falling trigger or both, we configure the those EXTI registers and also enable the mask register so that the pin gets to act as an interrupt. So that's all about the init function. Okay, so before understanding the other IRQ functions, first we will go to the device specific header file, and in that I have done only these changes in the header file. That is, I have defined some base addresses of something called as NVIC ICR, ICR1, ICR0, and ICR1, and some base address of something called as IPR. So in order to understand what is happening here is you have to go to the user guide, means the user manual, and in that there is a section called as Cortex M3 peripherals, and in that you have to go to the NVIC section. Since these are produced by Cortex M3, so that's why we are referring to the user manual. And in that you can see here different registers like NVIC ICR 0 to 7 means 8 registers, and ICR. So yeah, you can see their base addresses as here, and the description as interrupt set enable registers means if I want to set an enable, sorry, if I want to set an interrupt at that EXTI line, I need to enable that bit from this NVIC, means NVIC registers. So as you can see, it is a 32-bit register, meaning that each NVIC register can handle up to 32 interrupts, right? And since my STM32 Blue Pill has only up to 60 interrupts, so meaning that I would only need two such NVIC registers because 32 plus 32 64. That is enough to handle my interrupts in for my STM32 Blue Pill. For your board, you might need some more NVIC registers, but yeah, for my case, I only need two of them. That is NVIC ISCR 0 and NVIC ISCR 1. So that's what I have wrote here. NVIC ISCR 0 and ISCR 1. Since it is a 32-bit register, so the offset value is 4. So if the base address of ISCR 0 is this, then for ISCR 1 it will just get incremented by 4. This is the register for which if we want to enable the interrupt. But if we want to disable the interrupt, so there is another register called as NVIC ICR, and you can see the description as clear enable registers, meaning if I want to disable that specific interrupt, I will use this ISER register, and for the same case I would only need two of them, that is ICER0 and ICER1. So as you can see here there are only two of them, and the same, that is in ICER1 will have four more values than the base address, and I have made them as a pointer because these are addresses and I don't want the compiler to treat this address as a number, so I have typecasted it into pointer and wrote the volatile keyword so that the compiler doesn't optimize it. Similarly, there is a another register called as IPR, you can see here, which is an interrupt priority register. And for that, like each interrupt is having its own priority. Like suppose if I have two interrupts triggered at the same time, so the NVIC will get confused, like which one should I process first, which one should execute first. So to solve this problem, there is something called as priority, which is assigned by the programmer, meaning that if a interrupt is having priority, let's say 4, and if the other interrupt is having priority, let's say 7, so the lesser the priority is, the more advantage it has, means it will get executed first. So in this case, the interrupt with the priority 4 will get executed first, then the interrupt with priority 7. So that is what is done inside these NVIC priority registers. And as you can see, there are total 239 such interrupts, but means from PRI 0 to PRI 239, which means we can configure up to 239 interrupts. But as you know that Glue will only have up to 60 interrupts, so I don't need to go up to this 59. I'll just need something like something up to 20 or something IPR registers. But that's not the case. As you can see here, each IPR register can handle up to 4 interrupts. Means you might ask that these bits are like, it is a 8-bit, means each priority is assigned some 8-bit, like as you can see from here, 0 to 7, then 8 to 15, then 16 to 23, then 24 to 31. So you might say that I can assign an interrupt priority, means I can assign a priority 8-bit priority to each interrupt, like from 0 to 255. But that's not the case here, because the processor only reads the last 4 MSBs, means the last 4 bits. Like in this case, it would read only bits 7, 6, 5, and 4, only the last 4 bits, meaning I can assign each interrupt a priority from only 0 to 15. Even though I have a space to write 8-bit priority, but it won't consider the whole 8 bits, it will only consider the last 4 bits. So each interrupt is having a priority from 0 to 15, and in that only the last 4 bits, means suppose for this PRI 4n plus 2, it would only consider bit 23, 22, 21, and 20, only the last 4 bits. Okay, so I hope now you have understood that there are total 239 interrupts which we can give priority to, and out of, means even though I can assign 8-bit priority, means the processor will only consider the top 4 bits to give the priority. That is, each interrupt I can give a priority ranging from 0 to 15. So that's why this priority register is important. So this is the base address which I have defined in the header file here. And again, I have typecasted it to a pointer so that the compiler doesn't treat this as a number and treat it as an address. So once you have understand this, we can now go to the .c again and understand about the IRQ config. We can understand what is happening inside this driver.c file. As you can see here, there is a function called as GPIO IRQ config, and in that there are two parameters passed. One is the IRQ number, and another is whether we have to enabling or disabling that specific interrupt. So to understand IRQ numbers, we have to go to the reference manual. In that, again, to interrupts and events, and then NV controller, and this is, means that column you see here, that is of position, these are called as IRQ numbers. So as you can see, each interrupt is having its own IRQ number. For example, if I'm using EXT as 0 line, I'm using the IRQ, means it has some defined IRQ number as 6. If I'm using EXT as 4 line, it has a IRQ number of 10. And this number is fixed. That is, it is manufactured in that way so as to have a fixed IRQ number. Suppose if I am using EXTI 9 to 5, means this line, then it has a fixed IRQ number of 23. If I am using EXTI, where it is 10 to 15, um, here EXTI 10 to 15, it also has a IRQ number of 40. So these IRQ numbers are fixed. So what happens is, basically, it is not necessary that each IRQ means each interrupt will have its own priority. There might be case where the programmer might not have defined some priority to interrupt. Like suppose if two interrupts occur at the same time, like suppose if there is an interrupt from the CXTI line and there is an interrupt from something SPI2. So if I haven't given them any priority, so both of them will have equal priority by default. So now the NVIC will get confused, like which, if they are having equal priority, now how will he decide which interrupt to execute first? So then he will means he will focus on something called as this IRQ numbers. So since Pi2 is having a IRQ number of 36 and EXTI 15 to 10 line is having a IRQ number of 40, the lesser the IRQ number is, the more priority it gets. Meaning that, sorry, this meaning that the Pi2 interrupt will get executed first and then this EXTI interrupt will get executed. So means if the priorities are equal, then this type of clash is solved using the IRQ numbers. So that's where IRQ number helps. And in order to configure which type of interrupt we are using, we need to pass in the IRQ number. Since I am writing only for GPIO drivers, so I have to only pass in the IRQ numbers for the EXTI line. Like for EXTI 0, IRQ number is 6, for EXTI 1, IRQ number is 7, 2, 8, 3, 9. So in the .h file, I have defined those. These are the priority, means as I told about in the IPR register, we can give them a priority up to 0 to 15. So that's the priority we have defined here. And there is, it's in .h. Uh, there it is here. So as you can see, I have defined the IRQ numbers for them. Like if IRQ number for EXTI 0 is 6, IRQ number for EXTI 1 is 7, 2, 3, 4, 9 to 5, and then 10 to 15. So these IRQ numbers are defined in the device specific header file. So once you have the IRQ number, now you need to take the another parameter which is enable or disable. Whether the programmer wants to enable this interrupt or disable this interrupt. And as I have said here in the user manual, in order to enable the interrupt, we need to use these registers, that is NVIC ISER, and to disable the interrupt, we need to use this ICER register. So that's what we are doing here. If the EN means if this parameter is enabled, meaning that we have to configure the ISER register, right? So that's what we are using. Means since it is a pointer, we are dereferencing it and then changing the value in that register. And now you can see here there is like another if block for IRQ number. Like if the IRQ number is less than 31, then we will configure ISER 0 register. If the IRQ number is less than equal to 63, then we will configure the ISER 1 register. Now, as I said previously that since this is a 32-bit register, meaning it can handle IRQ numbers from 0 to 32. But if the number is more than means the if the IRQ number is more than 32, then I have to configure the another register, that is ISER 1. For IRQ number, I'll repeat again. If the IRQ number is from 0 to 31, then I configure the ISER 0 register. But if it is more than 30, means if it is more than 31, then I'll configure the ISER 1 register. And I don't need to configure register more than that, because at max the value can be 60, because that's the number of interrupts my STM32 has. So that's what is done here. Depending upon the IRQ number, we will configure whether the ISER 0 or ISER 1 register. And if it is not enabled, means if we aren't enabling the interrupt, then of course we are disabling it. So we are setting the ICER register, and it has the same logic. Like if the IRQ number is less than 31, we are setting the ICER 0 register, and if the IRQ number is less than equal to 63, then we are setting the ICER 1 register. Same logic for both. So in this function, basically what we are doing is we are taking the IRQ number as a parameter and whether we want to enable or disable it. If we are enabling the register, means if we are enabling the interrupt, we will be setting up the ISER register. And if we are disabling the interrupt, we will be setting ICER register. And depending upon the IRQ number, we will check whether which register we are means setting. So yeah, that's what is happening in the IRQ config. I hope you get it. The IRQ priority function. As you can see here, we have passed two parameters. Again, the IRQ number and the priority. So as you know that we can assign each interrupt a priority ranging from 0 to 15. That is only up to 4 bits. And as you can see, each IPR register can handle up to 4 interrupts. Right? I'll be attaching a image as in the video. You might see it now. So you can see there, like if I want to means IPR1 register will have another 4 interrupt configured, then IPR2 will have another 4 interrupt configured, so on. So in order to decide which IPR register we are configuring, that is totally dependent on the IRQ number. Suppose if the IRQ number is suppose 9, so I need to configure the IPR2 register, right? And in that I have to configure the bit from 8 to 15, as you can see in the image. So it is totally dependent on the I mean IRQ number, which IPR register I am configuring and which bits of that IPR register I am configuring. It's totally dependent on the IRQ number. So that's the mathematical logic we have written here in order to define means decide which type of IPR register we are going to configure and which of the bits we are going to configure here. So in order to know which IPR register we are configuring, we'll divide the IRQ number by 4. And in order to decide which bits we are going to configure, we will do the modulus of the IRQ number. And we can understand by taking an example. Like suppose if we want to configure IRQ number 14. So 14 divided by 4 will give me 3, right? Because since it's an integer, so it will round it off to 3. So I know that I need to configure the IPR3 register from this. And if I do 14 modulus 4, it will give me 2. Means I know that the second section of that IPR register I need to configure. I am not yet decided which bits I need to configure. For that, I'll multiply it by 8, as you can see here. Since the remainder is 2, 8 twos are 16, meaning that I will configure the means start configuring from the 16 bit to the another 23 bit, right? Means the 16 to 23 bit section I'll be configuring. So that's why I have multiplied by 8. Means take the modulus first and then multiply. You can like multiply here also, but I have written it here. So yeah, by dividing the number by 4, we will know which IPR register we are going to configure. And by taking the modulus 4, we will know that which bits of that IPR register we are going to configure. If you have confusion, I'll give you another example. Suppose we are configuring for IRQ number 10. So what will happen is we first we'll do 10 divided by 4, right? Which is 2. Means since it is an integer, it will round out to 2. So from that, I'll know that I'll be configuring the IPR2 register, right? And in order to know which bits of that IPR2 register I will be configuring, I'll do the modulus operation. 10 modulus 4 is 2, meaning that I'll be configuring the second section of the IPR2 register, right? There are total 4 sections, 0, 1, 2, 3, 4 total sections. In that, I'll be configuring the second section. And which bits I am going to configure, for that I'll multiply it by 8, meaning that 2 multiplied by 8 is 16, meaning that I'll be configuring from the 16 to the 23 bit. This section I'll be configuring. So I hope you get it now. Once we know which IPR register we are going to configure and which bits we are going to configure in that IPR register, we'll just add it to the base address. Like since it is a 32-bit register, it will have an offset value of 4. So if I do 100, means if the base address is suppose 100, and if I do it plus 1, then it will jump to the address of 104, right? Since the offset value is 4, meaning that it will go to the suppose if we are configuring for IPR1 register only. So this will give 100 plus 1, meaning 104. So it will jump to the base address of the IPR1 register. And as you can see here, I have written two lines for it. In first line, I am clearing this section. Like I have also written a comment here. In order to write a safer code, first we will clear that specific section, means whether it is section 0, 1 or 2, section 0, 1, 2, 3, this four section, out of which the one of the section we will clear depending upon the this prix value. And once it is clear, then we will assign the priority. As you can see in this line of code, we will assign the priority to the prix into 8, means we will shift it in by that much amount. Like, okay, I'll give one more example. Suppose if we are configuring IRQ number 5, so what will happen is IP 5 divided by 4 1, meaning I am configuring IPR 1 register, and 5 modulus 4 is also 1, meaning that I will be configuring the first section of the PR of the IPR 1 register. And which bits I will be configuring, that I'll know by multiplying it by 8, means 1 into 8 is 8. So I'll be configuring the bits from 8 to 15. So first I will clear those bits by using this line. I will clear those 8 to 15 bits, and then I will assign some, let's say the priority is 5. So I'll assign this priority, means the priority is 5. It will get left shifted to that specific bits, means it will now get assigned to 8 to 15 section. But as you know, I have told you earlier that the processor only consists, means only considers the last 4 MSBs, right? Only the last 4 MSBs it needs. Means if it is if the IRQ number is 5, then the 5 is now assigned, as per this code, it is now assigned to the 8, 9, 10, 11, these 4 bits, right? But the problem is the processor only considers the top, means the top 4 MSBs. So I think you might know now that I need to again shift it 4 times. Means the number 5, like in the example, as I said, the number 5 is now lying on which of the bits, 8, 9, 10, 11. But the processor only considers the top 4 MSBs of that specific section. So I need to shift it again. I need to left shift it again by 4 times so that it goes to the MSB section. Meaning that now my 5 will be on bit 15, 14, 13 and 12. These last 4 bits. So, and that will be considered by the processor. Means that will be considered as a priority by the processor. I know this is a bit complicated to understand. Okay, so the next function is IRQ handling, and this is quite easier compared to others. Here we will taking only one parameter, that is the pin number, and basically we will go to the reference manual first. Whenever an interrupt is triggered, there is a pending register in the EXTR line which goes high, and when this bit goes high, the NVIC sees this and checks if the processor is doing anything more important. If not, then this pending signal is then sent to the processor, and then this interrupt gets executed. So it's all dependent on this pending register. If the interrupt is triggered, this pending bit goes high, and once the processor executes this interrupt, we need to clear this pending bit in order such that it doesn't fall inside an infinite loop. Like, we don't want the interrupt to keep on getting executed, right? We need to only execute the interrupt when it actually needs to be executed. So for that we need to clear this pending bit. So the fun part is, in order to clear this pending bit, we don't write 0 to this bit. We instead write 1 to this bit. Yeah, sounds weird, right? But actually this is what it is. We will be writing, suppose if I'm using bit 8 as a interrupt. So once the interrupt is triggered, the processor performs this interrupt, and once it is performed, I will clear this bit by writing 1 to this bit, not 0. So that's what I'm doing here. I will be first checking that if the pending bit is high or not. Like, if the pending bit is high, I will clear it. And how I will clear it? I will clear it by writing 1 to it. But you can see that I have not used this operation bitwise OR. I have instead used direct equal to. You might ask why I have done this. This is because suppose if there are more than two interrupts triggered, like suppose along with bit 5 there is along with bit 8 there is also bit 5 interrupt which is triggered, right? So you know that both of these bits will go high, like this will also be 1, and the bit 5, this will also be 1. So if I do this operation, like the wrong operation, if I do bitwise OR instead of direct equal to, what will happen is this bit means I will be setting bit 8 as well as bit 5. Even though I don't want to set the bit 5, it will be mistakenly be set because I'm doing bitwise OR, right? You will be seeing a image there on the on something on the screen right now, where you will be seeing like if I do bitwise OR, so the bit 8 which will become 1 now, and the bit 5 which was previously 1 will also become 1. But the problem is now writing 1 to it means I am clearing that pending bit. So the processor will then clear the pending bit of this 8 bit and will also clear the fifth bit, which I don't want, right? I don't want the fifth pending bit to get cleared. Instead, I want to first execute that interrupt and afterwards I need to clear this bit. But it's getting cleared even before I look at that pending bit. So I don't want this, right? So that is why I am not using bitwise or I am using direct equal to here, because when I do this, only the bit 8 will get clear, not the bit 5. I mean, if you think like that, if I means using bit 8 as an interrupt, if I left shift 1 means if I left shift 1 8 times and then do direct equal to, so you will see that only the bit 8 will stay high, else all the bits will be 0. And now the processor knows that bit if bit 8 is set, I need to clear it, so it will then clear it. It won't clear the bit 5 now, meaning that my bit 5 is safe now. It won't get cleared unintentionally. So that is why I have used here equal to instead of this or equal to. So I hope you get it. This is all about the driver.c file. I have explained what changes we have done in the device specific header and this .c file. Still, I'll give you an overview. First, we start with the init function here. First, we saw that which type of means interrupt does the user want, whether it is rising edge or falling edge or both. Depending upon that, we configured the AFIO registers as per the pin numbers, and then we verified the which port does the user want to use, whether it is port A, B, or C. Depending upon that, we configure the EXTR register and enable the mask register, so on to enable that interrupt. So this is all done in the init function. Once this is done, then we went to this function irq config, where we use the nvic registers from the user manual, and to enable the interrupt we use nvic iscer register, to disable we use nvic icer registers depending upon the irq numbers. Then we set the priority to these interrupts, and this priority is being set using this logic. And then we like use some pointer logic. First we clear those section, then we set priority to that section, and then we got to know that only the top 4 msbs are considered as a priority, so I'll shift it again by 4 times. So this is how the priority is set. And now finally when we are handling that interrupt, we will basically clear the pending bit uh, from the pending register once the interrupt gets executed. So we will be clearing that bit by writing 1 to it, not 0. So that's all happened in the .c file. Now we will see two examples. In first example, we will be blinking, means we will be controlling an LED using button, of course, but using polling. And in another, we will be using our this interrupt logic to handle the LED. So this is an example of polling. Basically, we are not using anything we wrote about interrupt here. We will be directly, means as you can see here, here's a while loop which constantly tracks whether the button is pressed or not. And if the button is pressed, then we will write high to that LED. If it's not pressed, then we will write low. The problem here is we are constantly checking, means the processor is constantly performing that same operation again and again, which is taking more clock cycles, and due to which processors will not be able to do other tasks much more efficiently. So that is something we called as polling. So you can like see here, it's quite readable code. We will use like GPIO A pin number 0 for LED and GPIO A pin number 2 for button, and we will be constantly checking whether the button is pressed or not. Means If the button is means when I press the button, it is connected to ground. So as soon as I press the button, it will go to low, and as it goes to low, I will write the LED as high. And again, I have used that fake delay function which we used earlier. And if the button is not pressed, then we will keep the LED as low constantly. So this is what is done in the polling. And now it's the time where we use all the interrupt code we have written so far. Like as you can see here, the void delay, it is the same which we have used it earlier. The interesting part is this bottom part. Here we have defined the button interrupt, which is GPIO pin 4, and I have made it as a falling trigger so that when the button goes from a high state to low state, it will trigger an interrupt. And I have used an pull up internal pull up for this. And for LED, I have used a GPIO pin 5 with a speed of 2 megahertz. And since it's an output pin, I don't need any pull up or pull down. And yeah, since I'm using GPIO B, I need to enable the peripheral clock for port B. And you can see this line here, which is RCC AP2B or something. So basically, to understand this, we need to go to the reference manual again. And in the RCC section, there is something called as APB2 peripheral register. And you can see this bit 0 as AFIOEF. If you scroll down a bit and read this it says alternate function IO clock enable. So in order to enable means in order to access the AFIO registers, in order to make changes in those registers, we need to enable this bit because if this bit is enabled, then and only then the clock for AFIO is available. And once the clock is available, I can then configure the AFIO registers. Now, why was I using AFIO register? I was using it in init function, right? To make sure which EXTI line is acting as means which EXTI line is working for which port, whether it is port A, port B, or port C. And depending upon that, I was making changes in the AFIO registers. So for that changes to happen, I need to enable this bit so that the AFIO clock gets enabled, and hence I can configure the AFIO registers. So that's why I have written this line. And the comment also says that enables the AFIO EN bit because the interrupts we will be accessing are the AFIO registers. And then we are basically passing the address of these handlers to the unit. Once this is done, then we will call the IRQ config where we will pass the EXTI line like since we are using pin number 4. So you remember, right? In the start I told if I'm using pin 4, I need to use EXTI 4. If I'm using suppose pin 3, then I will need to pass EXTI 3. If I'm using pin 5, then okay, so if I'm using pin 5, then I can't pass EXTF5 because there is no such line as EXTF5. I need to pass EXTI 9 to 5, right? You can see in the header file also. Yeah, here. EXTF IRQ number 4, it has a IRQ number of 10. And then there is nothing called as EXTF5. There is EXTI 9 underscore 5, means 9 to 5. All these pins are given a single IRQ number. And this is done in order to save some pins. So yeah, that's what is happening here. And since I'm means then I call the priority function. And since I'm using only one interrupt, I don't need any priority. I just give a random number like 5. You can give 7, 8, 9, doesn't matter because it's a single interrupt, right? I can even pass nothing here, it will still work. So this is the priority. And then in the while loop, now notice that in the polling code, we were constantly checking the state of the button, right? But in this case, I will be just writing the LED constantly 0 and adding that fake delay. I'm doing nothing here like constantly checking something so as to keep my processor busy. So that's the main advantage of interrupt. I don't need to care about constantly checking the state of anything. So as soon as the interrupt is triggered, this handler function will be called. Now you might ask like, how did I know this name means the name of these functions? So for that you have to go to the startup file. There is a .s file here, and in that you can see this exti irq handler. So this is the name of that handler. Means this is the name of the function which I need to give, and you can see here as .weak means if I don't use this function here, like if I don't use this function, the startup file will include the default what we can say default line for this exti4 IRQ handler if I don't define here. So once I define this function here, this line will be ignored, and that's why it is a weak signal. So basically I overwrited the exti4 IRQ handler, and now this will be overwrite by this function. And once the interrupt is triggered, I need to make the LED high, right? So that's what I did here. I made the LED high, and once the once the process I wanted to do, like making the LED high, then I'll call the IRQ handling. And you know well why we are calling IRQ handling, right? To clear the pending bit, because we don't want the interrupt to constantly being called. So that's why we will be calling the IRQ handling once our desired output has occurred. Then we will call the IRQ handling. This will clear the pending bit, and the interrupt will get finished, and then the program counter will jump to the main function again. So that's what happening here. And this is all about interrupt. Once the code is uploaded, I can basically see the interrupt happening. Like when I press the button, it goes from high to low state, and that's when the interrupt gets triggered and it makes the LED high. And I've added some delay so as it doesn't occur in the debouncing state. So yeah, that's all.